Years ago, I was playing Sonic Origins, the remake of the original Sonic trilogy, and I was playing the special stages in Sonic 3, and something weird happened. Like, I wasn't sure that it was correct. Right here. Or looking at it from another angle, right here. If you never played Sonic 3, you might not know why this is weird. So just a brief recap for those who don't know. In the Sonic 3 special stages, you are tasked with collecting every blue sphere. If you touch a blue sphere, then it becomes a red sphere. If you touch a red sphere, you lose. And if you surround a square of blue spheres with red spheres, they all turn into rings. In the clip I showed you, we have a setup similar to this, where the perimeter is mostly already red. The game intends that if you cut through the middle, you get 2 squares of red spheres, turning both sides into rings. Now when we look back at the clip, only one of the sides is turning into rings. And I double checked with the original Sonic 3, and it does turn both sides into rings. Now, initially I just chalked this up to one of those inconsistencies with the remake. I mean, there are plenty of small ones, but they're ultimately inconsequential, so I just moved past it. But years later, I was asking myself, well, how would I implement the special stage algorithm? So I got curious, what is the algorithm Sonic 3 uses? Lucky for me, Sonic Retro already disassembled all of Sonic 3 and Knuckles, and as a result, I could just look at the code. So after about a week of studying that code, I am now able to present Sonic 3 and Knuckles' sphere to ring algorithm. To start, I want to go over some important memory addresses. Address F100 in RAM holds the map of the special stage. The special stage is 32 bits wide and 32 bits tall, resulting in a map that ranges from F100 to F4FF, with the numbers on the sides being relative to the start as opposed to an absolute address. Next, in ROM, there are 2 tables. The first table at AOCA holds 8 2-byte numbers. These values represent directions in the special stage, where 1 represents right, hex 20 represents down, and then hex 21 represents the sum down right, etc., etc. The second table at AODA holds 6 2-byte numbers, this time only representing the cardinal directions when left and not being duplicated. So I mentioned that the map is 32 by 32 bytes, but what are in those bytes? Each byte represents what type of sphere is at that position in the map. For this video, there are 4 values we care about. If the value is a 1, that is a red sphere. If the value is a 2, that is a blue sphere. If the value is a 4, it's a ring. Now, when you touch a blue sphere, it doesn't immediately become a red sphere. It goes into a temporary state with a value of 10 before actually becoming a red sphere. For the rest of the video, I'll be describing it as a touched sphere, and I'll be coloring it purple. Going back to the map and shrinking it down to make it easier to see, we have our next 2 memory addresses. Address A500 and A600 both represent 256-byte long lists, used by the algorithm as a queue and a stack, respectively. I call these the ring queue and the walk stack, respectively. These names will make sense when we see them in action. Here, I'm going to fill the map with an example state. In this state, Sonic has already touched most of the outer spheres. He just recently touched the sphere at address F133 and is now in the process of touching the sphere at address F132 to complete the loop. To the right is the actual code of the game, which I'll be using for a reference for the rest of the video. Though the code is real, the names are made up by me for ease of reading. Lastly, beneath the directions are the 15 registers of the Sega Genesis. The first 8, D0 to D7, are the data registers, and these typically hold, well, data. The last 7 are the address registers. These usually hold locations in memory. We'll start the explanation in the middle of the touch blue sphere code. This is the code that runs every time you touch a blue sphere. At this point in the code, the address A1 holds a location in the map of the blue sphere you just touched. And you can see, one of the first things the code does is turn that sphere into that temporary value I talked about earlier. Next, it jumps to a different part of the code used to turn the spheres into rings. The first thing the code does is set up some registers. It sets up A2 to point to the start of the map, and then it takes the address of the touched sphere and the address of the start of the map, and then stores their difference in D5. As a result, D5 represents the relative position of the touched sphere in the map. Of course, before turning spheres into rings, you should be checking if you should be turning spheres into rings. So the code has them jumping again to a different part of code, which is responsible for looking for those loops of red spheres. Similar to the last bit of code, it starts up by setting the register A5 to point to the start of the ring queue. From here, I'm going to skip ahead a bit. This bit of code is just doing some easy checks to make sure it's even worth running the code. TLDR, it checks the neighbors of the starting sphere to turn other touched spheres into red spheres and to make sure that there is at least one neighboring blue sphere. Next, it checks to make sure that the starting sphere is part of a line that is at least 3 spheres long horizontally and part of a line that is at least 3 spheres long vertically. So we finally reach the part of the code where it actually tries to find a loop of red spheres. This is done by trying to walk a path of red spheres and seeing if we can make it back to the starting sphere. To do this, it uses the walk stack to keep track of the path currently walked. To To that end, it uses A4 to point to the start of our walk stack, as well as using D6 to keep track of the size of that stack. Next, to keep track of which direction to check, it sets A3 to point to the start of the second direction table, as well as setting D3 and D4 to 0 and 6 respectively, acting as indices into that direction table. D4 and D3 will act sort of as a range of directions to check. D4 will represent the next direction to check, and D3 represents the last direction to check. If you look at the starting sphere, I will be demonstrating this range as an arc from teal to red with a circle representing the current direction being checked. Next, we set up D0 to represent the current position of our walk starting at D5. Now I'm temporarily going to switch to a separate example where there is no loop, because I want to demonstrate how the walk works independent on whether or not it finds a loop. So every time the code wants to take a step, it gets the current direction indexed by D4 and adds it to the current position D0, resulting in a new position representing our potential neighbor. It then reads what type of sphere is in the new position and checks if it's one of two types of spheres. Either a marked touched sphere or an unmarked red sphere. Now I'll get into what makes a sphere marked later. For now, the value of that sphere is blue, so we just skip ahead to the next neighbor. To get the next position, we subtract 2 from D4 to get the next direction, and make sure D4 is still at least as large as D3. We go back to the top, and we start again. Getting the next neighbor, this time it's actually a red sphere. Now, before taking a step in that direction, there's an additional check that only happens when the size of the stack is at least 2. For now, that's not the case, so we are free to take the next step. Before taking that step, the first thing we do is mark our current position. And now I can finally talk about what makes a sphere marked. Let's consider a potential red, blue, and touched sphere, as well as their binary representation. We want a way to keep track of which spheres have been processed by our algorithm in a way that maintains the type of the sphere. The best way to do that is simply by adding hex 80. Doing this, the most significant bit will be changed to a 1, making it a different type of sphere. So now we can check which spheres have and have not been processed by our algorithm. The best part, this can be undone by simply subtracting hex 80, making an easy way to simply mark and unmark a sphere. So the first thing we do in the process of taking a step is to mark the sphere at our current position. This way, the path won't be able to cross over itself. Now every time we want to take a step forward, we also want a way to take a step backwards, basically undo our step, in case we make a wrong turn. And this finally is where the walk stack comes in. Before taking a step, we want to record the current state of our position and the direction checking range. To do this, the code pushes the values at registers D3, D4, and D0 into our walk stack, as well as incrementing our stack size. Now for the rest of the video, I'll be compressing those 4-byte sections into a single block. So just keep in mind that each block is 4 bytes long, not 1 byte. Next thing we need to do is find a new range of directions to check. I could go over the code line by line, but I think it makes sense to look at more of a broad sense. The new lower bound is 2 less than the previous direction, and the new upper bound is 4 more than the new lower bound. There's also this additional and 6, which we'll ignore for now. Looking at a concrete example, let's say our last direction was moving downwards. In this case, the index of D4 holds the value of 6. By subtracting 2 from 6, we get 4, which is the index for right. Then, by adding 4 to that, we get an index of 8 representing left. And you can see, what this does is it defines a new range that does not go in the opposite direction of our previous step. In this case, the next possible directions are only left, down, and right, not up. Applying this formula to the other directions, we get similar results. The issues only really start to come in at the boundaries of this table. For example, if we moved left with an index of 0, then subtracting 2 from that ends up being out of bounds. Now this is where the and 6 we ignored previously comes to save the day. The process of bitwise ANDing is taking the binary representation of 2 numbers, lining up their bits, and then for each position, the output bit is 1 only if both the input bits are 1. In this case, the process of ANDing 6 results in zeroing out all of the upper bits, leaving 6 as the resulting lower bound, and then we add 4 to get a proper range. Similarly, if we move up with an index of A, even if subtracting 2 is perfectly fine, the later adding of 4 also moves us out of bounds. Going back to before adding 4, if we do the same bitwise operation with 6, the result ends up being 0, resulting in a valid 0 to 4 range. So no matter which direction we come from, we always get a valid range which does not go backwards. After the ranges have been set up, we simply set the value of D0, our current position, to the value of the neighbor we are moving to, finishing the step. Now we go back to the top and do the same thing over again. This loop continues, always looking for the next red neighbor to take a step towards. Of course, once the walk stack becomes 2 elements long, we have that additional check that we need to perform. First, we load the position of the next neighbor into D2. We then want to subtract that position from the position 2 steps back in our path. Finding the position 2 steps back is done by taking the register A4, representing the top of the stack, and subtracting 6 from it. Expanding the stack again, we can see that the 6th box from the top represents the position 2 entries back. The resulting difference is a vector of sorts between 2 steps back and the next neighbor. We then check if that difference vector is any of the unit directions, either 1 up, 1 left, 1 right, or 1 down. If it's any of those, we ignore this neighbor and continue. To see why this check is performed, we have to switch examples again. Skipping ahead to when this check matters, we see that when 2 steps back is right next to our next neighbor, it creates this tight 2x2 square that is not allowed to be considered part of the loop. So this check is performed to prevent that. Going back to our previous example, since this situation is not the case, we may continue stepping. Next important thing to talk about is what happens when we've checked every direction we wanted to check, but there are no red spheres to step towards. In the case that D4 becomes less than D3, the code does not jump back up, and instead falls through to this part of the code responsible for loading an entry back from the stack. This code pops the last entry that was pushed, reloading the last current position, the incoming direction, and the last lower bound, while also decrementing the stack counter. If the stack counter becomes negative, we know that we checked every direction from the starting position, and therefore every path, so we return, ending the algorithm. This isn't the case here, so we continue. We then unmark our current position to represent that the sphere is no longer part of our current path. Lastly, just like the code for getting the next neighbor, we subtract 2 from the current direction index and check whether or not it is less than the lower bound. If it is, jump back to the top of the popping code to pop the next entry. Otherwise, jump back to the start, looking at the next direction to check. In regards to just the pathfinding part of the algorithm, that is all there really is. If you've ever taken an algorithm class, this is a perfect example of a depth-first search or DFS algorithm. Basically going as deep or as far as you can with arbitrary choices of direction and using a stack to save previous states so you could unwind and check other directions. Fast forwarding the algorithm, we can see that in action, how it checks all possible paths of red spheres, going forwards and backwards, and ends when we return to the start and there are no more directions to check. Now, that's all well and good for finding paths, but the point is to look for loops. How does the algorithm know when there's a loop? And what does the code do when it finds a loop? Going back to our proper example, let's fast forward the algorithm until the point where a loop should be found. And here, we find that check for the marked touched sphere. Since we can't go backwards, and since the only touched sphere that can be marked is the starting sphere, we know that if we make it back to a marked touched sphere, we found a loop. Once we found a loop, we jump to this other part of the code used to handle the loop. Since when we close a loop, it's supposed to turn the blue spheres on the inside into rings. What this segment of code is responsible for is determining, well, what is the inside of the loop? Of course, before doing that, we save a bunch of registers so that we can use those registers and then restore them to continue the pathfinding code. First thing the code does is calculate the vector which represents the last direction in the loop. This is done by taking the last position, subtracting the starting position, then negating the result. Now I have an arrow on the map representing this vector. And though it's on the map, remember that the value itself is only the direction. Its position on the map is just a personal representation of where this arrow comes from. The value itself holds no positional information. Next, we set the address of A4 to be 6 bytes into the walk stack. This basically just points to the position in the second entry. By subtracting the starting position from the position at that A4 address, we get a vector representing the initial direction of the loop. What the code wants to do is basically rewalk the path of the loop. To that end, D3 will be used as a new current position register. The code reads the next position in the walk stack while incrementing the A4 register, takes that new position, then subtracts the current position to get the direction of that step. The code is trying to look for when that next direction is different from the starting direction. In this case, it isn't different, so we add the direction to the current position to move it, then jump back and load and check the next direction. This loop continues until it finds a direction that is different from the starting direction. Once it finds that different direction, there's an additional check to make sure that the last direction is different from both the starting direction and the new direction. This isn't the case here, so for now, we'll ignore it. Now that we have this new direction, we take that direction and then add it to our starting position. This will result in a new position which purportedly should be inside the loop. Then finally, we check if that position is a blue sphere, and if it is, we turn it into a ring. So basically at a high level, the code makes the assumption that the inside of a loop, relative to the starting position, is in the direction of the first turn, which in this square example makes sense. Now there's an issue when the starting position is in the corner of a loop. In that case, there is no direction that touches a blue sphere, and that is where that extra check we skipped over comes into play. Skipping ahead until we find the changed direction, we see in this case that the final direction is different from both the start and new directions. As a result, this check passes. So before adding the new direction to the start, we add the initial direction to the changed direction, resulting in a new diagonal direction. As a result, instead of checking a cardinal neighbor, it ends up checking a diagonal neighbor, resulting in finding a blue sphere and turning it into a ring. Going back to our main example, if ever you do find a blue sphere and turn it into a ring, we want to save the position of that ring inside our ring queue. Either way, we restore the registers we saved earlier and then go back to our pathfinding loop, checking the next directions. Now, because paths are inherently bidirectional, you'll see that when we return to the pathfinding algorithm, it ends up just finding the same path in the opposite direction. It doesn't really matter because we ultimately find the same inside, and because it's already a ring, we have nothing to transform. And just like before, we continue until we pop an empty stack and then return, ending this part of the algorithm. In case you became lost with all that jumping around, to get you up to speed, the code that we just looked at that checks for loops, that was helper code that we jumped to from the spheres to ring code. Now that we returned, we could continue with the rest of the code that turns spheres into rings. Well, more accurately, if that helper code did find a loop, we continue to turn spheres into rings. If no valid loop was found, we just stopped this code early as well. At this point in the code, A5 should point past the end of the queue. Now, we will eventually want to loop over every element within the queue, so to do that, we set up A4 to point to the start of the ring queue. This will act sort of like our current position in the queue. We also calculate and store the difference between the start and the end position and store that into D1. That will be used to keep track of how many elements remain in the queue. If A5 and A4 are the same, well then that means the queue is empty, which means the loop finding code could not find any valid loops. It also means D1, which represents how many elements remain in the queue, will be 0. If that's the case, we do nothing and simply just return to our starting code. Adding to the diagram, there should be a 1 next to the ring. I'll be adding a number next to each ring in the ring queue, which represents that ring's position in the ring queue. Since this is the first ring, it shows a 1. From here, the code reads the next position in the ring queue and sets D5 to that value, incrementing A4 in the process. Then, by using A3 to point to the first table of directions, we will continuously increment A3 and add each respective direction value to our current position to examine each neighbor of the ring. What we are ultimately trying to do is find other neighboring blue spheres. Once we found a neighboring blue sphere, we turn that sphere into a ring and add its position to the ring queue as well as incrementing D1. We keep this process going for each neighbor, seeing if it's a blue sphere and turning it into a ring and adding it to the ring queue if that's the case. Once we've exhausted all the neighbors, we decrement D1 to indicate that we have one less ring to look at, and then we look at the next ring in the queue. Before we continue, notice how, despite starting this loop with one element to check, we now have 3 more elements to check. I think the best way to conceptualize what is happening is to think of a queue as like a to-do list. Though processing each element removes that element from the list, in the act of processing, more elements may be added to said to-do list. Kind of like if you had a to-do list which involves doing the laundry. By doing the laundry, you end up adding folding laundry to that to-do list. Similar to the previous depth-first search, if you've ever taken an algorithm class, this is what is known as breadth-first search, or BFS. The basic idea is to have a queue of things to either check or do, which acts sort of like your to-do list. And when processing an element or task, instead of processing each sub-element or subtask immediately, you simply add each of them to your to-do list to check or do later. This type of algorithm is often used in minimum pathfinding algorithms or space-filling algorithms. In this case, it would be the space-filling kind, where we find all neighbors of neighbors of neighbors of blue spheres to turn them all into rings. We continue this loop until there are no more elements in the queue left to process, at which point all of the inside blue spheres should now be rings. All that is left to do is turn all of the red spheres into rings, and to do that, we do almost the same thing. First, we set A4 back to the start of the queue, so we can use it to loop over the queue again, and for each ring, we turn the neighboring red spheres into rings this time. The difference with this loop is that we don't add the new rings to our ring queue. We only transform the red spheres that are immediately touching a processed ring. As a result, the spread of rings stops at the red sphere border which contains the rings. Once that is done, we mark a successful ring transformation by playing the ring loss sound effect. Of course, you might have noticed that the touched sphere is still not a ring, and that is where the last little part of this comes in. The last thing we do before returning is setting the value of D1 to 1. Once we return, you can immediately see that after the call to the sphere to ring code, there is a BEQ instruction. Now, I've mostly avoided talking about specific instructions, as I think they could be needlessly pedantic and a pacebreaker, but I'll make an exception here. BEQ stands for branch if equal, basically a conditional jump instruction. Though often used with an explicit compare or test command, it technically checks if the result of the previous operation was 0. If no valid loop was found, then remember that the previous operation would have been checking the size of the queue, which would have been 0. As a result, the value of the last operation would still be 0, so the code just immediately returns. If, however, we do find a valid loop, then that last assignment, the one that set D1 to 1, will make this jump check fail. And only then will it execute the code that finally turns that touched sphere into a ring. And that is the algorithm in full. Now, I realize that considering how much jumping around there was, you might have gotten lost. So to help ground the flow of the algorithm, I'm going to give a brief big picture overview of the algorithm using a flowchart to help guide you. First, we set the value of the sphere that Sonic just touched to that touched value. We then call the function that handles turning spheres into rings. That function in turn calls another function which handles looking for those loops of red spheres. The first thing that function does is just checking some preconditions before we continue. It then uses a DFS algorithm to walk every path of red spheres starting from the touched sphere. Whenever it finds a loop, it jumps to code responsible for determining the inside of the loop and determining if that loop is a valid loop. It is done by rewalking the path, finding the first turn, then adding the direction of that turn to the start, and checking if the sphere at the resulting position is blue. If it is, we turn it into a ring and it's considered a valid loop. Either way, we continue searching every path of red spheres. If we find another loop, we rerun that code and continue searching more paths. Once we are done walking every path, we return to the previous function. If we found a valid loop, then we fill the loop with rings. Either way, we then return again to the first function, at which point, only if we succeeded in finding a valid loop do we turn the touched sphere into a ring. And with that, the algorithm ends. With the basic example out of the way, let's take a look at the example from the start of the video, where we cut across creating 2 loops. Skipping ahead to the pathfinding part of the code, we see that it starts off by simply following the outer square, creating a loop around the entire thing. However, the inside arrow in this case does not point to a blue sphere, it points to one of those middle red spheres. So as a result, this loop doesn't count. And then, after backtracking, it eventually finds that middle path, ultimately creating a short rectangular loop on the bottom. In this case, that corner check kicks in, and as a result, it ends up finding the blue sphere that is bottom right from the start, and turns that into a ring. Afterwards, it backtracks to the start, and it heads off to the right. Of course, it then just ends up re-finding that bottom loop and ends up not really doing much there. But then after backtracking and going up, it now finds that upper loop. Similar to before, it finds the blue sphere up right from the start, and turns that into a ring. After a bit of backtracking and then retreading old paths, it eventually stops. Once we get back to the ring filling algorithm, each of those 2 initial rings end up expanding their own respective domains. Then each of those 2 domains end up turning the red spheres next to them to rings, and then the entire square becomes rings. Now, I can't speak to how Sonic Origins handles this and why it's different, but at the very least, this highlights how in Sonic 3, it doesn't just check a loop, but it checks every loop. So for now, we can give a point to Sonic 3 for handling the case that Origins fails to handle. However, when I was attempting to understand the algorithm, I had a series of questions about the correctness of the algorithm. My first concern is how the algorithm chooses which direction is inside of a loop. I mean, sure, in a square case, it makes sense that the first turn goes towards the inside, but is it not possible for the first turn to point away from the inside? And in that case, the inside arrow would be pointing to nothing, so no rings would be created. Could that actually be the case? Like, if we had a setup like this, we can see that after it completes a loop, the first turn arrow points away. And this is also true for the loop going the opposite way. Would this really not work? So I booted up Sonic 3 and Sonic Origins, and, well... So it seems like Sonic Origins actually fixes an issue from Sonic 3, so point to it, I guess. And in retrospect, this seems almost like an obvious oversight, right? Okay, wait, hold on, something else just occurred to me. If it's possible for the inside arrow to point outside, what happens when there are blue spheres on the outside? Would those spheres turn into rings? Could you get rings by making a loop from inside instead of from outside? Like, if we look at this setup here, with an inner loop and that little lip, we see that because of that lip, for the loop that starts by going up, the first turn would be to the left, pointing directly to the set of outer blue spheres. If we then fill out the rings, we can see that it ends up turning the entire square into rings. I mean, does it actually work like that? Going back to the game. So it's clear that Sonic 3 is a little janky, not always doing what you would expect. Not only is it janky, that jankiness is often used in speedruns of Sonic 3, like this example from YouTuber Sound Defense RB.
Time for Jackie, how are you doing? Today has been utterly unspeakably cruel as I continue to get on world record paces and then have them shattered.
And by simulating that setup, we can see not only why that works, but also see what the game is doing and how it even decided to turn those spheres into rings. However, looking at the simulation, another concern arises. The DFS algorithm used for finding paths seems kind of inefficient. Like, it seems like if you give it too much open space, it ends up having a bad habit of just wandering all over the place. So the question is, can we push that to the extreme? Like, in this example for instance, where its freedom for choosing to turn into and out of the inner square ends up with an exponential number of possible paths, which the algorithm is forced to try all of them. And this can be made even worse considering that this algorithm has the potential on executing each time Sonic touches a new blue sphere. So the question is, can we do something similar in Sonic 3? And what would happen? So yeah, after the first loop, with each blue sphere Sonic touches, the algorithm starts taking longer and longer to complete. And honestly, I don't know what black magic Sonic Origins does to not have this issue. For all I know, it's just more powerful hardware, but nonetheless, I tip my hat to the developers. They ended up fixing a lot of the jank, making the game act a lot more reasonable. It still sucks that I didn't get that first layout correct, but I think that's a fair price to pay. I mean, I can't ask for everything. Though, there is one last thing I want to test. In the Endless Blue Spheres minigame, there is this one weird layout. What the game expects you to do is jump over one of the red spheres and cut across, just like the first example. This setup was just different enough that I was curious to see how Sonic Origins handled it, and, well, the result was not what I expected. I have no words and no explanations. So yeah, Sonic Origins is still not perfect. Well, now the obvious next question is, well, how does Sonic Origins work? Well, unfortunately, I cannot answer, as, well, I mean, there's no code for me to look at. That being said, if there's sufficient demand, I may make a part 2 going over the Blue Sphere code in Sonic Mania, as that has been decompiled and there is code for me to read. In the meantime, if you like this video, make sure to like and subscribe. I'm likely going to be making more programming-related videos, so stay tuned for that.